In this lecture, the 23rd of our series, I'll be switching attention from the focus on individual atoms and small molecules to the collective behavior of atoms and molecules, the properties of the materials in our everyday world. A great principle of material science, one that we experience every day, is that the temperature and pressure induce changes in the state of chemical compounds. I have two objectives in this lecture. First, I'm going to describe the various states of matter, including the familiar solids, liquids, and gases of our everyday life, and also the less familiar plasma, which actually makes up the most abundant part of our universe, the stars. Then I'm going to discuss the remarkable and the ever so useful ability of materials to change their state, especially under changes of temperature and of pressure. In the past two lectures, we've been focusing on three common types of chemical bonding. We have ionic bonding, in which electrons are transferred from one atom to another, thus forming ions. We have metallic bonding, in which several atoms share electrons in a negative C in which they're positive centers floating about. And finally, covalent bonding, in which a small group of atoms shares the electrons locally. We're now going to focus on more distinctive physical and chemical properties of materials in their bulk state. That is, in large collections of atoms and molecules that we experience in our everyday lives. And the key theme of all material science is that all the properties of materials that we experience are the result of atoms and how they bond together. The most immediately obvious property of a material is its state. Now, state is sort of a vague term. It relates primarily to a substance's volume and its shape. The states of matter, solid, liquid, gas, and plasma, are basically an everyday manifestation of the submicroscopic organization of atoms and molecules. In our discussion of organic molecules last time, for example, we made frequent reference to solid, liquid, and gaseous arrangements of atoms. And you may recall that larger molecules were more likely to be condensed into solids or perhaps liquids, and the smaller molecules were more likely to be volatile, becoming gases. Well, the behavior of our planet, indeed the presence of life itself, depends critically on the coexistence on these various states of matter, solid, liquid, and gas. Solids are the first state of matter I want to discuss, and they have a more or less fixed shape as a consequence of a three-dimensional arrangement of relatively strong and rigid directional bonds. Solids include all the hard objects like rocks, wood. They also include a variety of flexible materials, things like aluminum foil and cloth. Plastic wrap's another example of a solid that can easily change its shape. Now, you can think of the structure of a solid something like a ball and a stick model, like Tinker Toys, in which the sticks may be somewhat flexible, but the arrangement of the balls relative to each other is fixed because they've been linked together in some sort of permanent long-term way. There are three different classes of common solids in everyday use, and these are crystals, glass, and polymers. And these three different types depend on the regularity of the bonding of those atoms. In crystals, the atoms occur in a regularly repeating pattern, the same atoms over and over and over again. And to think about a crystal, you could imagine a box, maybe something like a shoe box, which can stack top to bottom, side to side, front to back, like you might find in the storeroom of a shoe store. Now imagine that in each of these boxes, all exactly the same size and shape, are the exact same arrangement of a few atoms. And that's sort of what a crystal is like. For example, in table salt, the common mineral halite, you have an arrangement that's a cube. The tiny box is a cube, and the atoms are one sodium for every chlorine. So each box contains a few sodiums and a few chlorines, and those cubes repeat over and over and over again, and they form beautiful cubic crystals. By the same token, we have the beautiful mineral fluorite. Often comes in purple colors or otherwise colored. And here, the box again is a cube. In each box, you have one calcium and two fluorines to form CaF2. And again, the crystal structures are very commonly perfect cubes. That reflects that internal structure. Now, many common minerals, including gemstones, beach sand, computer chips, have SiO bonds. And in those, you have tiny boxes that contain one silicon and two oxygens in every box. And again, they form perfect crystals. You may have seen power crystals or the magic crystals that you can hang around your neck for good luck. Those crystals are usually quartz. Many rocks, many ceramic materials are polycrystalline. They contain many small crystals that are interlocked in a complex way. For example, the common rock, granite, contains interlocking grains of a variety of type. You see in a rock like this some colorless grains, which are quartz, the common mineral of silicon and oxygen. And then there's also feldspar, a mineral with potassium, and some dark minerals as well. And these different crystal grains are interlocked to form the rock. That's typical of most common rocks. By the way, my scientific background is as a crystallographer, and our job in crystallography is to determine the atomic structures of these materials. And the way we do it is very simple. We take a crystal, just like one of the crystals of the minerals I've shown you, and we mount it in a beam of X-rays. It turns out that X-rays diffract. They bounce off crystals in a very specific way. They bounce off the planes of atoms. So if you have a plane of atoms and another plane above it, X-rays come in, and at certain angles, they reflect off. The angles tell us how far apart the planes of atoms are spaced. Furthermore, the intensity of those X-rays tells us which atoms are located inside the box. And so we determine the size of the box and the shape of the box and what atoms are in it. That's the crystal structure. The second kind of solid is a glass. And glass is a general term for a solid that doesn't have a regular crystal structure. In most glasses, you have an immediate local environment that's quite predictable. For example, most glasses have silicon with those atoms surrounded by 4 oxygens. And virtually any time you find a silicon atom in a glass, you're going to find 4 oxygens in the immediate vicinity. But if you go a couple atoms away from there, it's very difficult to predict what you're going to find because of the irregularity of the glass structure. Most common glasses are predominantly silicon and oxygen, and most glasses also have a small amount of other elements. And those other elements can drastically change the property of the glass. Some elements make the glass brightly colored. Other elements, for example, lead, make the glass bend light in a more dramatic fashion. And so most cut glass or crystal chandeliers have leaded glass to give you that very beautiful display of colors in a prismatic effect. Pyrex glass, which is very special for cooking because it doesn't expand, it doesn't contract when it's heated, has a little bit of boron in it. There have been a lot of recent efforts to produce a new class of glasses called metallic glasses. If you can imagine a metal that actually has a glass-like crystal structure, then you can imagine a metallic glass. And these materials might have very special properties if they could be invented and used in a large-scale manufacturing process. The third kind of solid is plastics. And as I mentioned in the last lecture, plastics are made from polymers. Plastics are formed from intertwined chains of carbon-based atoms cross-linked by hydrogen bonds. Now, as a result, plastics have a very predictable structure in only one direction, along that polymer chain. If you have one small molecule linked to another, linked to another, linked to another, you can pretty much predict the structure along the chain. But side to side, you can't predict how the fibers are going to be interwoven. So it's kind of a one-dimensional structure, if you will. Plastics can be quite flexible. Indeed, they can be all different sorts of materials. You've seen plastic shopping bags that are incredibly strong and thin. Plastics make virtually all the materials that go into modern sneakers, from the rubber-type soles to the fibers that make up the cloth of the sides and the laces. And we have a wonderful variety of plastics that go into the various tapes and the other kinds of adhesive materials that we use in our everyday life. Another important class of solid materials, which combines glasses and plastics and crystals, are called composite materials. Now, composite materials constitute a growing class of solids that combine 2 or more different materials together to give enhanced properties. And you've all experienced these. One of the most common is plywood. I want to do a demonstration. Those of you on audio tape are going to have to imagine this, but I have two pieces of wood. One, a solid piece of sturdy poplar. The other, a piece of plywood, exactly the same size and shape. The plywood is made of very thin layers of wood that have been glued together. And the trick here is that they've been glued together so the grains run at right angles. All wood has grain. If you take a piece of poplar, just a pure piece of wood, place it between two bricks, and just give it a slight tap, it splits quite easily. Not a very good structural material if you're going to be hitting the wood with a piece of hammer. But the plywood, the exact same size and shape, even though it's made of softer woods, I can hit it as hard as I want to. Nothing happens. That's because plywood is a strong composite material, a material that enhances the property of wood simply by placing the pieces of wood with crossed grains. There are other kinds of composite materials we use all the time. For example, reinforced concrete uses steel rods in solid concrete. Fiberglass uses fibers that are often in an epoxy resin. So once again, the theme of fibers running through a strong, solid material. And even our teeth, our bones, are composite-like materials made of mineral-type substances plus organic fibers, polymers. And all of these different composites are examples of solids. Okay, we shift now to the second state of matter. That's liquids. Liquids are collections of atoms or molecules that can change their shape while they retain their volume. It's such a familiar phenomenon, it's hard to think that it's anything extraordinary, but the fact is a liquid, it's holding its volume, but it's changing its shape. And that's good water. Well, at the molecular scale, liquids behave sort of like a bag of flour. There are forces that hold those liquid molecules together, but they're very weak forces, so the molecules are free to move past each other. And you recall from the last lecture the two types of forces that are involved here. One's the weak van der Waals attraction, and the other is hydrogen bonding. These cause the molecules and the atoms of liquid to be attracted to each other so they don't go flying off into space, but not so strong that they form a rigid crystal or a solid. By the way, the forces between these molecules lead to a phenomenon called surface tension. The reason that water forms little beads and droplets is because all the molecules tend to clump together. It's not a solid, but you do see a shape forming when a drop of water forms, so you can see that tendency to form hydrogen bonds. Turns out that water is the only common liquid in nature. There's a little bit of petroleum, a few places there's a little bit of mercury metal, but it's predominantly water on our planet. And its physical properties, the physical properties of this liquid, have played a key role. It plays a key role in the shaping of the Earth's surface through erosion and weathering, plays a key role in the formation of life. Now, an intriguing variation on the theme of liquid is something called a liquid crystal. This is a liquid that's formed of polar molecules. These are molecules that have a positively charged end and a negatively charged end. And in the absence of an electric field, polar molecules of this sort just form a normal liquid. But what's neat is what happens when you apply an electric field to a liquid crystal. Because there's a positive and a negative end, all those molecules line up suddenly, just like they were in a magnetic field, just like a bunch of compass needles. And so you have an alignment of molecules, and as a result, the properties of the liquid change quite dramatically. Remember, properties are the result of the molecules and atoms and how they're bonded together. Indeed, what's primarily dramatic is the change in the optical properties. So you can use liquid crystal displays where the properties of the liquid change. If you apply a field, you get a dark material. If you take off the field, you get a light material. And so you can have liquid crystal displays in that way. The third state of matter is a gas. A gas is nothing more than a collection of atoms or molecules that expands to fill whatever volume is available. There's no fixed volume, there's no fixed shape. We talked about the inert gases, the last row of the periodic table, the last column of the periodic table. Those are composed of individual atoms. Recall that there are other gases which are just small molecules. Oxygen, O2, nitrogen, N2, CO2, that's carbon dioxide, and so forth. These are all simple gases formed from small molecules. If you could magnify a gas 1 billion times, what you'd see was the individual particles flying around all over, sort of like the ping pong balls in a state lottery game. Gas pressure itself is the result of the collisions of these particles and the wall of the container. So if you blow up a balloon, what you're seeing is the air pushing against the elastic part of the balloon. And of course, if you pop the balloon, what you're seeing is an explosion because of the air pressure pushing outward. That's simply the collective force, the combined push of all those different atoms and molecules bumping against the walls of the balloon. We now come to the fourth state of matter. This is called a plasma. And a plasma is a strange state of matter indeed. A plasma is produced when gas is subjected to extremely high temperatures. I want you to think about how this might happen. You have gas molecules colliding into each other all the time. But as you raise the temperature, the speed, the velocity of those molecules gets higher and higher and higher, and the collisions are with ever more force. And indeed, when you get to a high enough temperature, the gas molecules, when they collide with each other, start stripping off electrons. An atom or a molecule with electrons removed is suddenly a charged particle. And you then have a sea of electrons that are also charged particles. Positively charged atoms and molecules, negatively charged electrons forming a sea. Does that sound familiar? Have you heard of that before? Indeed, a plasma has many properties like metallic bonding. Only in this case, it's sort of a gaseous state of a metal. In the atoms and molecules being ionized carry electric charge. The electrons carry the electric charge. And so, for example, you can pass a current. An electric current can pass right through a plasma. Furthermore, a plasma can be confined by a strong electromagnetic field. Because electric charged particles are influenced by magnetic fields, you can imagine confining a mass of plasma in what's called a magnetic bottle. But this bottle has no walls. It's just strictly an electromagnetic field. It's an astonishing thing to see a glowing incandescent gas or plasma confined in just pure space. But that's exactly what happens in these magnetic bottles. Plasmas are the most abundant state of matter in the universe. And the reason is because plasmas form stars. Virtually all the visible matter we see when we look into the night sky are stars, and those stars are entirely made of plasma. So that's 99.99% of the visible universe. We don't think about plasma as much in our everyday life. We think of solids, liquids, and gases, but there you have it. We do, however, use plasmas in a few technologies. For example, in fluorescent light bulbs, the bulb is filled with a very tenuous gas, and when an electric current is passed through this, the gas ionizes, and you have a plasma. Also, the electrons in the individual atoms and molecules in this tube are jumped up into excited states. And when that happens, they drop back down and emit photons, and that's the visible light we see from a fluorescent light bulb. Okay, now that we reviewed the four states of matter, solids, liquids, gases, and plasmas, let's consider the remarkable ability of matter to change states. It can change from solid to liquid, from liquid to gas, and back again. These transformations are very familiar. They include things like freezing and melting, boiling, condensing. And these changes are most commonly observed in our everyday world as a result of changing temperature. Well, water is the obvious example. Water is a liquid at room temperature, but it transforms to ice, to a solid in our freezer. And then it transforms to a gas when we boil it on the stove. These are changes that we make use of all the time. Now, if you could heat up water high enough to several thousand degrees temperature, you'd also turn water into a plasma. So that's the fourth state. All of these changes induced just by changing temperature alone. We're quite lucky on our own planet that water maintains a liquid state most of the time. Because one thing most biologists are convinced of, you can't have life without water in the liquid state. This is because water dissolves solvents. It becomes the medium for life. And all known life forms depend on liquid water. Well, we've talked about changes of state, and a candle provides an interesting and a more subtle demonstration of the same sort of phenomenon. This harkens back to the last lecture when I talked about how a candle burns. Recall that the candle wax itself is typically a carbon-based molecule. It's about 20 carbon atoms long. These molecules are large enough with those 20 carbons to form a solid under room conditions. But when you light the candle, you're increasing the temperature. And when you increase the temperature, phase transformations take place. The first thing that's happening is the candle wax is melting right at the tip, right at the base of the candle. And that's roughly at a temperature of 100 to 200 or 300 degrees centigrade. But as that liquid is pulled up into the wick, the flame itself heats up the liquid. It gets hotter and hotter, and the liquid becomes a gas, and it's the gas that you see burning at the hottest part of the flame. Solid, liquid, gas, all as a function of temperature in this beautifully working device, this simple device called a candle. Petroleum refining, which is such an important part of the chemical industry, uses the exact same technique. Petroleum, that is crude oil that you take up from the ground, is an incredible collection of thousands, tens of thousands, hundreds of thousands of different organic molecules all mixed up together. And yet we want to use relatively pure compounds, gasoline or natural gas and so forth. And so the process they use to distill, to refine petroleum, involves using temperature. You've probably passed by some of those chemical plants with dozens of tall towers. Those towers are distillation columns. They're hot at the bottom. They're cooler at the top. And the way they work is this. You pump in, for example, crude oil at the base, and that's heated up. At the various stages, you have different materials that are gases. The very hottest part at the base, you have relatively large molecules that become liquid or become gas, and those molecules flow off at that point. The other molecules, the lighter ones, rise to the top, and at various stages of the column, different molecules come out. The lightest at the top, the smallest molecules at the top, the heaviest at the bottom. So, for example, you might have natural gas flaming out of the very top of that column. You might have propane and butane coming out somewhat below it, candle wax coming out from the middle, asphalt coming out at the bottom. Changes of state don't necessarily have to use temperature. That's the commonest way we do it in everyday life. But pressure also can induce changes of state. Pressure is a fascinating variable. Pressure is defined as a force per unit area. You apply a pressure anytime you step down on something, anytime you push a button, anytime you write with a pen, you're applying a force to an area. You're exerting pressure. Now, the uniform high pressure that you experience when you go diving, where water is pressing you from all sides, that's called hydrostatic pressure. It's a kind of uniform pressure from all sides. The atmosphere exerts a uniform pressure on us of 14.7 pounds per square inch. And you have to dive down about 30 feet in water to double that pressure. By the way, if you have pressures that are a lot less than atmospheric pressure, less than 14.7 pounds per square inch, we call that a vacuum. And vacuums can also induce phase transitions, as we'll see. If you lower the pressure, water boils at a lower temperature. And you may have heard that if you're in Denver, Colorado, for example, it's difficult to boil eggs because the water doesn't get hot enough to cause the polymerization reaction to change the egg chemically. If you take water high enough, to a high enough elevation, it'll boil at room temperature. Now, what might surprise you is that if you raise the pressure on water, you can actually go the other way. You can turn water as a liquid into water as a solid. What's more, this high-pressure form of ice is actually a different crystal structure from the normal ice that we experience at room temperature. It's a much denser form of ice. The H2O molecules are packed together in a much more crushed and compressed way. So simply by varying pressure, you can freeze water. The way scientists do this in the laboratory is really interesting. They use something called a diamond anvil cell. This is an incredibly elegant device that involves two diamonds that are facing each other. They have little flat surfaces. You take a sheet of metal and drill a hole in it. That becomes a chamber to hold your sample. So you have a bottom flat surface that's diamond, a circular cylinder of metal, and a top surface that's diamond, and you squeeze down on the sample. With devices like this, the diamond anvil cell, you can achieve pressures of hundreds of thousands, even millions of atmospheres, just by tightening screws. So this diamond anvil cell is the real workhorse of modern high-pressure research. For example, looking in the diamond anvil cell, you can watch water freeze. You can watch it turn from a liquid to a solid, and then change from one solid form to another, just by varying pressure. One of the interesting discoveries of modern high-pressure research is that every solid, every material becomes a solid at sufficiently high pressure. Water becomes solid at 10,000 atmospheres. But hydrogen gas, oxygen, all other materials become solid if you take them to high enough pressure. One of the research projects I was involved in some years ago was to study the crystal structure of hydrogen, of all things. Hydrogen normally a gas, but if you take it to 50,000 atmospheres, it turns into a crystal. And we actually determined, using X-ray diffraction, the crystal structure of those hydrogen crystals. Well, the variation of the states of matter with temperature and pressure can be beautifully illustrated on a phase diagram. This is a graph of immense visual power. The phase diagram of water is an excellent example. At any given combination of temperature and pressure, water is either a solid, or it's a liquid, or it's a gas. So each region of this phase diagram that has pressure on one axis and temperature on the other axis can be so coded, either as a solid or a liquid or a gas. Now there are certain lines on that pressure-temperature graph along which two states coexist. For example, solid and liquid coexist along the melting line. That's 0 degrees centigrade for water at room pressure. And also at one specific temperature and pressure called the triple point, you get solid and liquid and gas all coexisting stably simultaneously. For water, it turns out, the triple point occurs at about 0 degrees centigrade and 6/1000ths of an atmosphere. And there's another interesting point. When water in the gas phase and water in the liquid phase become indistinguishable at the critical point. The critical point for water occurs at about 374 degrees centigrade and 220 atmospheres. And it's intriguing that those conditions actually exist in places on the ocean floor. By the way, in a graph like this, plasma would be much, much higher temperature. It would be at thousands of degrees. I want to summarize this lecture by reviewing these four states of matter. We have solids, materials that have a constant shape and volume. And solids can occur as crystals, or as glasses, or as plastics. We have liquids, materials that have a constant volume but can change their shape, like water. And then we have gases, materials whose shape and whose volume just expand to whatever available volume there might be. These are the three common states of matter in our everyday world. And then, of course, there's plasma, which forms the stars. These states of matter can transform one to another through the application of temperature or, surprisingly, through the application of pressure. And such changes of state are easy to illustrate on a phase diagram. But as we're going to see in the next lecture, this is only the very beginning of phase diagrams. To me, by far the most astonishing effects of high pressure and high temperature are phase transformations, where one solid turns into another. And that is the subject of the next lecture.